All right, here we go. Keep going with our steel lecture here in a couple minutes. Uh, I think that the exams went pretty well. I think everybody turned one in. That's a good start. I briefly flipped through Gradescope. I didn't spend too much time on it. I'm trying to learn how to use Gradescope at the moment here, but I'm hoping this week to grade it and get back to you guys as soon as possible. I will be assigning a homework sometime today on Monday. To probably be due in a week that has to do with steel tension members. We also have a lab associated with steel tension members that hopefully Jaden will be able to carry out. It's directly related to what we're going to be covering today. Um, I think that's about it. Again, I'm going to have regular office hours. You guys can stop by and ask me any questions and talk to me about any concerns and stuff like that that you might have. I think the next one I have scheduled is today at 2 o'clock during a regular scheduled time. I would also say I'm probably gonna post something online. What I'm gonna that link to get a hold of me is someplace that you could go. I'm just sitting by my computer most days, and if I'm there, and you can enter that room even if I'm not there, and you can send me a chat or do something like that. And if I'm there and don't have anything else going on, not recording a lecture or something like that, I should be able to just log on and talk to you, even if I don't have a scheduled office hour. So. Stay tuned. I might make an announcement here. I'm okay doing that with structures too. Dynamics is a different case when I got 200 students floating around. I don't know if I want them poking in at all times. But, anyways, let's keep going with the steel design stuff. Like I said, it's a different beast. What we're going to introduce this idea of today. We're going to introduce this idea of limit state design. We're going to have these different limits on how we expect these members to fail, and we're going to find the weakest link, and that's going to control our design and control our capacity. So the lecture thus far on steel has just talked about, right, the introduction to steel, pros and cons, material characteristics, what the different shapes are and what they're used for. And then today we're going to start the actual design, right? The first thing that we're going to talk about the design of is steel tension members, okay? We don't have concrete tension members, right? There are some out there, but concrete's really bad in tension, and so usually don't use them as tension members. But there are ways that you can come up with a tension member with concrete, but it involves pre-stressing or post-tensioning. And in fact, that is what failed, if you recall, that pedestrian bridge in the pedestrian bridge in Florida that failed a couple of years ago. That was actually a concrete tension member that failed as part of this truss. But I think we'll spend a little bit. We'll take a look at that a little bit later. It's kind of an interesting case on what happened in that collapse. But we'll do that at a later time. So right now, this is kind of a unique to steel design in particular compared to concrete design is this idea of steel tension members. And you might be asking yourself, well, what do you mean like this? Sometimes there's things that are just loaded up in direct tension, right? Just like, oh, I need to hang something from something else, right? And uh, that would be a steel tension member, right? But more often than not, it'll be part of a structure, right? And so an example would be a truss, right? This truss would have certain members would be in tension. I believe like this guy would be in tension, right? And that guy being pressure, this guy would be in tension, that guy would be in tension as you go across here, okay? And so, oh, what's that? Go up. Yeah, that guy would be in tension right there. You'd have a big compression coming up like this, and that guy would have to go into tension there. But anyways, you could use structures one concepts and stuff like that to determine where your tension members are and stuff like that. We're just going to be talking about the design and the members. And so typically our designs are going to be, right, you're going to give it some sort of specimen like this, and we're saying, oh, here's the load that's applied to it. I'm not really going to do a full-on truss analysis. Might have that as part of a homework, but not in well, maybe we go take home exams. Maybe it'd show up in a take home exam. But the point is, it's the design of a tension member. Okay, it is spread out. Where you find the stuff we're going to talk about is kind of spread out throughout the entire ASCE or AISC document. Chapter D, chapter J4, and chapter B4 is kind of where these things come from. okay, that we're going to talk about below, okay? And again, this is the first time we're going to start talking about this idea and this concept of limit state design, right? We're going to look at an axially loaded member such as this, right? An axially loaded member such as this, and we're going to talk about, well, if I apply a load on it, how is this thing going to fail? Well, it can fail in multiple ways. And what we do is we calculate the capacity in each of those ways, and the one with the lowest capacity is the one that controls design. That's your weakest link in your design, okay? So the limit states that we have to consider, for tension members are these. Okay? And the next couple of the next subsections here spend a little bit more time talking about each of these things. But one of the first ones is yielding of the gross section. Okay. And I'll write these down and we'll talk about what each of them are in a second. So yielding of the gross section. We also have fracture of the net section. Right? And then the last one is block shear. Okay. And like I said, we're going to spend the next few sections diving into each one of these things in more depth. But just from the beginning, or just I'm going to give you an idea what each of these things are. So yielding of the gross section, that's kind of what I have drawn. I've drawn here. And so I have drawn here. Oh, I'm going to back that off a little bit. Make room. That's just... All right, so if I've got a member like this, and I'm pulling on it like this, okay, so if I've got these two members that are attached to each other, I got like some steel plate or another steel bar, and then I've got my tension member like this that's attached to it with some bolts right here. If I pull on that in this direction right here, one thing that can happen is it can yield out here. That's one of the failure mechanisms, right? And when it yields, it doesn't actually break. What it does is this thing right here, it gets excessive deformations. This thing starts stretching out a whole bunch, okay? And that could be considered a failure mechanism. If something deflects too much, right? It has, this thing, it stretches out 3 inches before failure, and it yields all along the length as we go along. That's bad, right? It hasn't failed yet, but it has failed in the sense that it's not usable because this thing has excessive deformation out in this region right here, okay? And so it doesn't actually break at that point, okay? It doesn't actually break. The next one, this fracture of the net section, is another mechanism in which something can fail, and that's what I have drawn here. Same idea is if I'm loading this sucker up like this, the same loading mechanism, what can happen is as I'm pulling this direction, you just rip this thing into 2 pieces. Okay, and this half stays put, and then this half goes to the right. Right, that's kind of what I have drawn in this picture right here. So this big chunk kind of pulls off to the right. Right. And that's obviously that is an actual failure, right? And that it actually breaks into 2 pieces, and you can see, and the difference kind of here. Look here, this one has to do with the gross area, yielding of the gross area, and this is fraction of the net section, right? And so what that's saying is like what'll happen when you start pulling on this thing, right? Either it's going to yield out here, right, where you get this excessive deformations, or it's going to break around the holes. And the reason it's going to break around the holes is because the area is smaller around the holes, right? It's more concentrated. This big force right here is going to be concentrated around these holes, right? Over here, you have the whole gross section, and then here, it's going to be more of a problem because, right, you have a reduced area because you have bolt holes through it, right? And so you might, if you're paying super close attention, you might be like, well, what about yielding of the net area, right? And so actually what'll happen is if you start pulling on this thing, it will yield here first, right? You have a reduced section, right? Your steel member is smaller around these holes, right? You've basically subtracted out the area of holes. So it's going to yield right in here first. But if you recall what steel does, where I have that, right? Steel goes like this, right? There's a stress strain response. It goes, and then it goes up like this until ultimate load. And so it's going to yield around those holes first, but then those holes will go through strain hardening. So it'll yield here, and then it will go through strain hardening, and it'll stop yielding. Okay, and then it could spread, right? It could spread it might yield out here before it breaks across that next section. But eventually, so it yields here first. Eventually, you'll get up to this point right here, or you might get up to this point right here where you hit your ultimate FU up here at the top, right? And so when that happens, that's when this thing will break, is when what I have drawn in the black right here, when that area right here reaches the ultimate, right, with that P divided by that area, when that hits FU, this thing could rip. Okay, but I don't know what's going to happen first. I don't know, is it going to rip across that net section first, or is it going to yield across the gross section? And so what we do is we have to calculate the capacity of both of those. Okay, so those are two of the primary failure mechanisms that we're going to see, right? Is yielding out here, or the thing's going to rip into two around these holes. The third one, which we'll talk about and explain what it is right now, but we're not going to calculate the capacity. Calculating the capacity of this is a little bit more difficult. Beyond the scope of this class, it will be in a steel design class in the future, and it's more of a connection design and a little bit less of the member design. Okay, and so we're going to cover that at a different time. So this is the same type of loading scheme here, where you've got, a plate. In this case, the plate's attached to a wall, and then we've got this other plate that's attached to it, and we've got it bolted like this, and we're pulling a load on this. Okay, and so for a block shear type failure is what you see here, right? It's different than this, right? Because it's not just rupturing across the net section. If that was the case, it would just rip straight through like this, right? In the block shear, it rips through like this, then it goes over this way, then it goes this way, then it goes this way, and then it goes this way. And so this big chunk that I've outlined in red, that's what rips off and goes to the right. And you can see that it's kind of a block of material kind of rips off. Same thing. The other thing that could happen, so it could fail that mechanism, or it could fail in this mechanism, as we showed in this, right? The inside, in this case, that big chunk would come out. In this case, this big chunk would come out, right? And so there's two different mechanisms that it could fail for block shear, right? In order for it to fail in block shear here, you'd have a tension failure here, and you'd have shear failures at these locations, and then another tension failure here. For this case, you'd have shear along these lengths, and you'd have tension along this length, right? And so even within the block shear, you would have to check different capacities, right? You'd say, okay, is it going to fail in this mechanism, or is it going to fail in this mechanism in block shear? And again, calculating the capacity of these are a little bit more involved beyond the scope of this class, but really involves shear and tension in these locations, or shear here and tension at this location, and the capacity equations have that built into them. Okay, another thing, just to picture what's happening there. That's not YouTube. Where's YouTube? All right, here's YouTube. Here's a picture of what block shear would look like. Sometimes students have difficulty imagining what's happening there. Let's see, block shear. Yep. All right, this is just a visual of what's happening with block shear. You pull on that, and boom, big ol'. That's the second case that I showed you on the previous page. Right, just gonna show you, or boom, where the inside rips out. Okay, and so again, that's kind of more on the connection designs, a little less on the member designs. We're going to focus on that. Oh, also, by the way, I just showed it for failure. On the previous page, I just showed it for the failure of the member that's attached to the big plate. The plate can also fail in the same mechanisms, and that's what it's showing here. In this case, it's the plate that failed and not the plate that failed and not the member that's attached to it. So really, in this particular case, there'd be 4 different mechanisms that you would have to look at, right? Because then now you could also fail like that, where it rips off the middle part of the plate that it's attached to, right? And so you'd have all of those limit states that you would have to calculate, right? That's how you know what that looks like.
Specialty flat plate pieces, such as stiffener plates, column caps.
Okay. All right, so let's dive a little bit deeper into what yielding of the gross section is and fracture of the net section, right? How you calculate those capacities. And when we do this in the lab, basically what we're going to do in the lab is we just got a steel plate that has holes drilled in it, and we're going to pull on them, and we're going to witness it rip through. I mean, we're going to introduce this little concept in a minute. It could, well, yeah, we'll get to that. If you have multiple holes and they're staggered and stuff like that, things get a little more complicated. But I guess I'll wait and talk about that later when we dive into it. So let's look at this failure mechanism first, yielding of the gross section, and see how we calculate that capacity. So yielding of the gross section, I think I've updated my notes a little bit, so you may not have these equations. You can jot those down really quick if you don't have those previously. Or if you don't have those in your notes, just depends on when you downloaded the notes that I posted. All right, so yielding of the gross section, right? So what we're going to do, first of all, what we're looking to do, let me put this up here. We're going to have an equation, right, PU. We have to make sure, I'm going to write that, yep, I'll do it right here. PU has to be less than or equal to phi PN. Right? Ultimately, that's what has to this right. This is still LRFD design. We have to make sure that our factored axial load is less than our factored axial load capacity. Our demand is less than our capacity. PU here is a factored load. It has a 1.2 times the dead load plus 1.6 times the live load, and then PN is our nominal capacity, and we have a phi factor to reduce the capacity out front, or strength reduction factor. Okay, again, this is going to account for our uncertainty in our ability to predict the capacity. It's going to account for the amount of ductility. You have a more ductile response, you're going to get rewarded with a better phi factor, and so on. So ultimately, that's what has to happen. And so in the next couple of days, we're going to look at calculating PN. We're going to calculate MN, and we're going to calculate the axial load capacity. This is the tension capacity. We're also going to look at the axial load capacity in terms of compression members as well in the coming days. But right now, let's talk about calculating PN for a tension member. So yielding of the gross section, right? So this is a phi PN. This equation right here, if we're going to calculate the capacity, that's what we do. The yielding of the gross section, we can calculate the capacity as being Fy times Ag. Fy is the yield stress of the steel. You multiply it by the gross area of the cross section, and that gives you a PN, right? Ooh, I left out the phi here. You listen, let me put a phi in there. And this should have a phi t. You can't drop that phi t, so that would be in there as well, right? And so you want to get the capacity, just Fy times Ag. Right? That makes sense. Fy is the stress. You may take the yield stress, you multiply it by the gross area. It gives me the axial load, and then I multiply it by a phi, and that gives me the axial load capacity. It gives me the phi PN for a tension member. Okay. Phi in this particular case, right? This is a ductile failure, so the phi is 0.9, right? Because this is a ductile failure. So you get rewarded for having a ductile failure. So in this particular mechanism, we use phi is equal to 0.9, and Ag is the gross cross-sectional area. Okay, and typically you can look this up in dimension tables. And AISC. Sometimes you could just calculate. If it's just like a plate with two different dimensions, you can calculate the gross area. Okay, it's just the total area is what it means by the gross area there. But also, if it's like a wide flange member that you have that you're going to be using as a tension member, if it's a wide flange, then look it up in the table. That's one of the things that shows up in that DIM table in your AISC member. Right? You remember the dimension tables? You look that up, and there's all the members throughout the entire document. And you look that thing up, and you could look up area is one of the things that you can look up. Okay. So that's it, right? So that if you want to calculate the capacity for in terms of yielding of the gross cross section, that limit state, this initial limit state, you just take Fy times Ag and multiply it by phi t. Okay, and phi t is 0.9 because of ductile failure. Done. Right, that's a pretty straightforward calculation for the capacity. Okay, and then the next one, right, is fracture of the net section. Okay, this is, fracture of the net section is the next one, right? This is where we're going to rip the thing into two pieces. Okay, so how do you calculate fracture of the net section? Right, so what you do is you calculate this capacity first, right? And then you come down and you calculate this capacity. And then the one that's the smallest is the one that controls, right? So how do you calculate fracture of the net section? Well, you take phi t times fu times AE, right? So instead of using Fy, right? Instead of using Fy is down here, right? In our stress strain response, Fu is the ultimate stress, right? And this is where it's actually going to break, right? It's going to yield around the net section first, but then it's going to go, and then when it actually fails is when it gets up there. So in this particular case, this is a brittle failure. When this happens, the thing rips into two pieces. There's not much warning. And so we get a phi factor. Right, so there's that equation. We get a phi factor of 0.75 instead, right? We don't get rewarded with a 0.9 like we did above because this could be a brittle failure. So we end up with a phi factor of 0.75. Fu, we just mentioned that. This is going to be this is the ultimate stress. You can look this up in one of those tables, okay, or it's given to you in the problem statement. But that's the ultimate stress, right? And that's beyond what Fy is. This is where it will actually break at, okay? AE, and this is where things get a little bit complicated, right? AE is the effective net area, is what we call that. Yep, let me see here. Yep, effective net area. There's a lot of stuff going on with AE. I'm going to move these drawings to the right a little bit. Make that red. Okay, it's the effective net area. So it's not the net area, it's the effective net area. And this is equal to, it's going to be equal to, I'll make this black. AE is equal to, I'm going to do an arrow here. AE is equal to, and line that up. I'm trying to be as clean as possible here. AE is equal to AN times U. Okay, so AN down here, this AN is equal to, oh man, getting messy with my notes here, but I'll get it here. It's the effective net area. AN is the net area. I didn't write what U was. U over here, we're going to dive into this a little bit in a second, or in a few minutes here. U is the shear leg factor. Got a little bit of a rabbit hole that we're going down here, right? You're like, oh, this is pretty easy. I got it. This is just phi is just Fu times AE. Fu is just the ultimate stress. AE, though, is the effective net area. How do you calculate the effective net area? Well, you take the net area and you multiply it by the shear leg factor. Okay, well, what is the net area? Well, the net area, AN, all right, we're going to talk about each of these components. We'll talk about what AN is, and we'll talk about what U is in a second. AN is equal to the gross area, AG, minus, this is my own variable I've added in, A holes. It's one of my favorite jokes. Fortunately, you're not there to to, or you're not here with me so that I could hear you laugh. I think that it's funny, okay? But now I'm just sitting, at this point, I'm working in my little home office just all by myself, and I'm laughing to myself that I just wrote a-holes on here, okay? But I think this is, you don't see this variable in codes, right? And I think that they've gone out of their way to make it more complicated instead of calling it a-holes, which it really is. It's the area of the holes that are taken up, okay? Or they're missing from your cross section. So it's going to be the gross area minus the a-holes plus T, which is our thickness, times a Stager factor. Okay? And we'll talk about what each of those are in a second. So let's talk about what a hole is, right? So this is what that is what my net area is, right? So again, this rabbit hole, it's FU times AE. AE is AN times U. U is the shear leg factor, which we'll talk about in a second. AN is the net area, and how you calculate the net area is your gross area minus the a-holes plus T times the Stager factor, okay? And so we'll keep going with that. So what is this? What do I mean by this net area, okay? And what do I mean by the area of a hole? And so what I'm trying to show is, or I guess what I'm showing here is what I have shown in this drawing. By the way, I made this drawing. I am pretty excited. I'm pretty pleased with myself that I was able to draw that. Right? You guys have seen my drawing, but look at this. Look at this son of a gun. Right? That's beautiful. Very proud of myself. Okay, so what I have shown here in this red, right? When I have what I've got in the red right there with these cross, right, that I'm showing again right there, that is what the net area is. Okay, that right there is what the net area is, right? And what it is, if this whole thing would be the gross area, all the way across would be the gross area. But since I have a hole in there, right? So this would be like if I was looking down on it, right? I'd have a bolt hole going through it. That bolt hole has reduced my area, right? It's reduced my overall area. The overall area is this, but I have to subtract out of it the area of a hole, right? My a-hole. If I had a couple of these things, there'd be multiple a-holes in there, right? And that is reducing my area. And so I need to calculate this total gross area, or sorry, the total net area. And so what it ends up being, you say the a-hole is equal to the diameter of the hole times the thickness. Okay, and that's well, I'll put up times in there so you can see diameter. Oh, I should put diameter of hole times the thickness. Okay, and so you can see that that's this area that you're subtracting out is that right there, right? So that right there is the area that gets subtracted out, and you can see that's the diameter right there times the thickness is what that area is. What it is not is if I'm looking down on this thing, like so if you're looking at this thing from above. Oh man, if you're looking at it from above, oh man. From above, it's not this area, right? Let me make that a little bigger, right? It is not, it's not that area, right? It's not the area of the hole, right? Like if you're looking down on it, it's this cross-sectional area, which ends up being this diameter times the thickness, right? And if you had multiple in there, you would subtract out multiple a-holes, okay? What else? Oh, let's talk about this diameter of the hole. This can actually be a little confusing as well. So the diameter of the hole is equal to diameter of the bolt, okay, plus 1/16 of an inch. 1/16 plus 1/16. Well, it would be a total of 1/8. Okay, and so what this is for, right? So that makes sense, right? You know, if I give you the diameter of the hole, right? Then you just use the diameter of the hole, right? That'd be part of the problem statement. If that's given to you, that here's the diameter of the hole, right? It's a three-quarter inch diameter hole or something like that. Then you just use that. But if for some reason the problem statement gives you the diameter of the bolt that you need to use, right? And this might happen in a design. If they give you the diameter of the bolt, well, then the diameter of the hole that the bolt fits through has to be bigger, right? It can't be exactly. So if you have a three-quarter inch diameter bolt, it doesn't fit into exactly a three-quarter inch diameter hole, right? So you have to increase the size of it, okay? And so what this is, 1 of the 16ths is for tolerance. Okay. That just makes sure, what I mean by tolerance, it just gives a little extra room, right? You give it a little extra room so that bolt will fit through that hole, okay? And then this one, there's another one floating around. One's for tolerance, and they come from 2 different sections of the code. And unfortunately, I don't have that in front of me right now, what sections of the code those come from. And this one is for damage, right? If for some reason you're in the process of drilling or punching the holes, right? And if you may have seen that in that video, if you didn't, you should watch that video because it kind of, how can I do this? Oh, dang it. Watch this. I'm going to delete that. Okay. Oh, man, I got a runny nose. Oh, hold on. Okay. Yep. Okay. So that's what I was talking about. I was talking about this. All right. So we're talking about calculating the area of a hole. It's the diameter of the hole times the thickness. What's the diameter of the hole? Well, it's the diameter of the bolt that's going to be used plus a 1/16 of an inch just to make sure it fits, and then another 1/16 of an inch just in case you're drilling or punching that hole. You might damage the steel around it. And if you damage the steel around it, it's not going to be effective at resisting the loads you're applying on it. And so, to be conservative, we ignore the fact that there's a little bit of steel there. Okay, so that's we're accounting for that extra damage or the damage that might have happened there. Okay, so we're almost there, and we're almost to the point right there. But the last thing that we do have to talk about is the Stager factor. Oh, and then I also want to present how the code presents it as well, or talk about how the code presents it. What the code does is, like I said before, you're not going to see the gross area minus A holes plus T times the Stager factor, which we're going to talk about the Stager factor in a second. We got to come back to what a shear leg factor is as well in a second. But you're not going to see a variable like this. What the book does is it says AN is equal to WN times T. Okay. And then the book says, or the code says, WN is equal to your width minus diameter of holes plus a Stager. And there's certain cases where this just doesn't really make sense to do it this way. Okay, we're not. So this is what the code does. Okay, in some cases that doesn't make sense. Like if you have an angle, for instance, having an angle in there, trying to use the book's definition of what the net area is, doesn't make sense. Well, let's take a minute to see. So basically, what it says is it's going to take this width. That's the overall width from here to here, right? And it says, what's the effective width? Well, the effective width is going to be this W minus the diameter. Minus this diameter of the hole. Okay, and if you have multiple, it's multiple holes. So you're going to have minus that diameter right there. Okay, and then I take the effective, so that's your effective width. And you take your effective width and you multiply it by the thickness, and then that gives me my effective area. Right, you end up in the same place. But where, again, what it's not going to be as effective is if I have an angle, for instance, right? If I have an angle like that, so being able to call this thing an effective width doesn't really make sense because it goes like that and then that total area. Whereas if you do it this way, you take a gross area, it'll take into consideration that you have a leg here and a leg here. But either way, just wanted to be clear that the code has a slightly different definition of what the net area is, but officially that's what that effective net area is. Okay, so now we're on to talk about what the Stager factor is. What is the Stager factor, and what is it for, and why do we care about it, right? And again, this is part of calculating what the effective area is. We need this shear factor floating around, and then ultimately we care about what the effective net area is because you multiply that by FU, and it gives you your PN, and you compare that PN to this PN of the yielding of the gross section. It'll tell you which mechanism it's going to fail based on which one's the smallest. Okay, so what is the Stager factor for? So you imagine these two different plates. This is exactly what your lab is going to be, except for we're doing it with three holes instead. You have a steel plate, you put 2 holes in it, right? And then I apply a load on it, and you look to see what its capacity is going to be, right? And so in this particular case, this AN, the net area, is going to be AG, the gross area, minus 2 A holes, right? Because I have 2 holes in there. So if I wanted that effective net area, it's what I have shown in red right there. And it's just going to be the gross area minus the area of 2 holes, right? And that's the cross section. That's looking this way what the area of those holes are, like we talked about above, right? So that's what your net area is. But then imagine, and so in that case, this thing's going to rip like this, right? It's going to rip. And it'll come down and go and it'll rip into 2 pieces like that, okay? But you could imagine if I have these things staggered, it could fail in 2 different ways, right? One, or actually 3 different ways. It could go like this, right? Just rip through one hole like that, or it could rip through this hole over here. And if they're the same size hole, they're equal. You don't have to calculate 2 capacities there because if they're the same size hole, it'll be the same value, right? And so in that case, your AN, if it was going to be one of those mechanisms, it would be AN is equal to AG minus 1 A hole, right? That could be one mechanism that it failed from, right? Or, make this green here, it could do this. It could go, it could rip through 2 holes, okay? Up here, obviously it's going to rip through 2 holes, right? Because they're lined up. Here, though, they're not lined up. So it's not clear if it's going to rip through this one or if it's going to rip through those, okay? So, and that's where that Stager factor comes in, is it's trying to account for that. So in this particular case, AN would be equal to AG minus 2A hole, right? That would give us, right? That would tell us that. But then we have it, right? That's what this would be, right? If they were lined up, it would just be AG minus 2A holes, but they're not lined up, right? There's more steel to rip through because those holes are staggered. It has to go down like this, and then it has to go all the way over here, and then it's going to go down here. Versus here, it just rips straight through these 3. So this, I guess, this length right here is different than this length right here, and that's what that Stager factor is in there to account for. It's to account for the extra steel that needs to rip through this thing because it's staggered. Okay. And so what that would look like is we add on that Stager factor that you saw above. This would be plus, we call that Stager times the thickness. Okay. And so what you do in this particular case is you calc both of these. Calc both and smallest controls. Okay, that's how you end up doing this thing. You calculate both of those. So within all of this, this is a little mini limit state within all other limit states, right? Is it going to rip through, if you had them staggered like this, is it going to rip through 1 hole or is it going to rip through 2 holes, right? We don't know yet, right? And so what is this Stager factor, right? That Stager factor is there to account for that additional area that the steel has to rip through, okay? But how do we calculate what that Stager factor is? Well, here it is right here, right? This is based on geometry. I haven't actually worked out to see if it's exactly geometry or if it has some empiricism built in. My guess is it has some empiricism built in. But this is how you go about calculating that Stager factor. Okay, that Stager factor that goes right here, right? That Stager factor that goes right there in our calculation is SI squared over 4GI. And then you have to sum these up for however many holes you have, right? So this is summation of SI squared over 4GI, right? And again, you have to sum it up over all of the stagers that you have in there, right? So in this example right here, if I was applying the loads on this plate like this, right? If I was applying that load, and say we're going to look at it ripping through 3 holes, right? Is it would rip like this. There you go, and over to here maybe, and then over to here, and then down, okay? So in this particular case, just to illustrate what SI is, right? SI in this case, or I guess S1, I should say, would be this distance. It's the distance parallel to the load. Move this. Right, this is going to be S1 is the distance parallel to the applied load, okay? And then your G1 would be this. G1, okay? So that's the S1 and G1. G is the perpendicular to the load, is the distance perpendicular to the load. The gauge is what that stands for, and the S is the spacing, okay? And that's the parallel to the load. But then that's only one of them, right? And there's another one here that goes from here down to here. That would be G2, right? And then this distance here would be S2. Right? Since we have 2 stagers in there, you'd have to sum those things up. Okay, and then so for this Stager factor that I've drawn right here would be S1 squared over 4G1 plus S2 squared over 4G2. Okay, and you add those things together, and that would tell you what the total Stager factor was here. So however many stagers you have is how many of these things you add up. So here's an example of those. So we have 3 holes, you have 2 S's and 2 G's. If you have 4 holes, you'd have 3 S's and 3 G's. Okay. The other thing, right, just to come back to this. So those are what your stagers are, right? For this particular example with 3 holes, you'd have to look at, right, is it going to rip, right, just going to get used to playing with this thing. Is it going to rip through here? Is it going to rip over here, come back here, and then down? Or could it possibly go here and then over and then down, right? Or could it go here and then over and then down? Or could it go, well, it could do one hole too. It could go through any one of these. So I'm running out of colors here. You can go and rip through one hole. What else? I think it could even do one more. It could maybe go here. Oh, I already used that color. Make it this color. It could be pink. Over here, and then over here, and then down. So you get the point. You'd have to calculate the net areas for all of those cases, right? We don't know. We have no idea until you calculate. Sometimes you can apply some logic to it and go, oh, clearly if it's going to break through 2 holes, it's going to break through this, right? If you have two lined up, if these 2 were lined up, we know that it's going to rip it through 2 holes before it ripped through like these 2 holes, for instance, right? Anyways, it's sometimes you can apply some logic, right? So you do have one of your homework problems is going to be something that has like 8 different holes in it, and then you pull on it, and then you have to calculate the net areas for all the cases and figure out which one it is that it's going to fail in. Okay, this is I think a fun little exercise. So you can see the complexity of. So you got to figure out, is it going through 1 hole? Is it going through 2 holes? If it's going to go through 2 holes, which 2 holes? Or is it going to go through 3 holes? Right? We don't know. And that is actually what we're doing in the lab, and that's what you're going to do in one of your homeworks as well. But then each one of those things, you calculate a net area. The one with the smallest net area is the one that's going to control. So if it ripped through 3 holes and that was your smallest, and you rip it through 3 holes, you include all your stagger factors, then we know that that's going to be that failure mechanism. Okay, and so that is what you use for the net area, right? That'll be accounted for when we calculate this net area. That's where that stagger factor comes in. The last thing we have to talk about is this shear leg factor, which is U, that's floating around. What is the shear leg factor used for? Okay, so to illustrate that, we're going to talk about, here's a plate. Okay, same idea, big old plate, and we have a big old plate down here, and then we have this plate that's attached to it, and we're applying the load. In this particular case, what I have drawn here are little welds off to the side, so maybe make note of that. Those are welds. Right? Versus if I weld it just on the end like this. So I've welded it on the side versus welding it on the ends. You can imagine if I take it and I apply the load right here, if I look at the stresses that are on this member, right, they would look like this. Right? They'd be greater near the ends and less near the middle. Something like that. This is what those stresses would look like. Right? The reason they would look like that is because I'm holding, right, the way that I have this thing, I'm holding onto it on the sides. And so I'm pulling it right down the middle, right? But near the ends here, it's going to be stressed more because that's where I'm attached, where it's attached to the wall, right? Where it's attached to the wall, it's going to attract more of the load, right? And so you can imagine if you're pulling on this thing, right, it kind of, the inside, well, it would deflect kind of like this, right? The outside would be attached to the wall and the inside would move up. And so it would look like this. And what that would amount to is stresses that look like that, okay? And in these equations up above here, the equations up above, this assumes it's the FU across the entire length, right? You take FU and you multiply it by the effective net area and it gives you the total force, right? That assumes that this thing is stressed uniformly across the whole thing. It assumes the whole cross section has been stressed to FU, but that's not the case. It's not always the case. Here would be an example where I've attached just the sides. It's not uniform, right? Its stresses near the outside are greater than the ones on the inside. If you move far away from that connection, if I move far away from that connection, this is what my stresses do become uniform. They do end up looking like this as I move away. That delay is called shear leg, right? It starts out, and you'll see this if you go into structural engineering, you'll see this a lot in a bunch of different places. It's a concept that comes up a lot, but near where the connection is made, it's ununiform stresses or non-uniform stresses. But as I move away from the connection, it becomes uniform stresses. Okay, and that process, but that delay, that leg is called a shear leg factor. Okay. Or it's called shear leg, that delay between here and here. But to account for the fact that if I have an eccentric connection, this is an eccentric connection, I'm only attached to the sides. If I have an eccentric connection, I get penalized a little bit, right? My U ends up being less than 1, right? And so if you look back up into that equation, that U right here is less than 1, and so it reduces my net area, right? And it's because you're going to get penalized a little bit because you're not evenly distributing it, right? It's to account for the fact that this out here is going to hit FU before it's uniformly distributed. This is what that equation assumes. That equation assumes that it has uniform stress across the whole length. But really, that's not the case when you have an eccentric connection. In those cases, your U ends up being less than 1. The other type is this guy over here, right? In this particular case, right away, the way that I'm holding on to it, I'm uniformly holding on to it at the end here, right? I'm saying, yep, I'm going to uniformly hold on the end of this thing to resist this load right here. And so instead of attaching to the sides, I've attached to the bottom. When I attach to this bottom right here, it's going to be uniform. And so right off the get-go, right, my stresses are uniformly distributed. As I move out here, they also are uniformly distributed. Right? And so in that case, my shear leg factor is 0. I'm sorry, not 0. It's equal to 1. My shear leg is equal to 1 in a case where I've uniformly distributed those loads, or I'm holding it in a way that's not eccentric. Okay? And so, sure, it's less than 1, and this one's equal to 1, but where do I actually find and calculate what this U actually is? Well, you do that in table D 3.1 and commentary. Okay, and commentary for that section is where you do that. And so let's look to see what that section is. Okay, and actually overall, we kind of see what chapter D is about, right? Let me see here. Yep, we'll get down to U in a second. There's that table. Okay, so just to back off a bit, okay, before I get into exactly what that U is. So this is chapter D. Okay, chapter D, this is coming from your specifications. I should also note that my PDF that I have for this code is actually from the last code, so the page numbers might be slightly off. The chapters are fine, but the page numbers, you see the page numbers on my notes, they might be a little bit different than the page numbers in your book. Okay, so this is chapter D, design of members retention. So this is under specifications. So if you open up your manual and then you find the thing that says spec, okay, and it's kind of near the back, you flip it open to that tab, and that's where all these chapters for the specifications are at. And if you look up chapter D, it specifically is for the design of members for retention. Okay, and so it has some initial stuff. So how is this? What do they cover in this chapter? Right, it starts out just with some basic information up here at the top. The slenderness limitations we're not going to use or deal. These things are in there just to make sure your members are transportable. If they're super slender, they'd be really hard to move, and so this just puts a limit on that. Okay, but then here we go. Tensile strength. How do we calculate the tensile strength for tensile yielding? It's going to be what the design tensile strength (ppn) and allowable tensile strength. So this is for ASD. This is for LRFD. We're going to deal with LRFD over here. Of tension members shall be the lower value obtained according to limit states of tensile yielding in the gross section and the tensile rupture in the net section. So it's going to be one of those two, right? And again, there's going to be blocks here, but that's going to be in connection design. It's not going to be in this chapter D. So how do I calculate the yielding, right? It's Fy times Ag. And phi is 0.9. And again, this is for allowable stress design, but we're going to do this guy over here on the left. Okay, so for tension rupture in the net section, Pn is equal to Fu times Ae. Phi is 0.75. Okay, Ae is the effective net area. Ag is the gross area of the member. Fy is the yield stress. Fu is the specified minimum tensile strength, and that's the ultimate strength. Okay. When members without holes are fully connected, when holes are present to the member with welded connections and another. Okay, so then the effective net area. So the next chapter D3 talks about what is the effective net area. Well, it's the net area times the shear leg factor. Okay, and it goes on to talk about what those shear leg factors are, and here they are. This is D3.1. This is where our shear leg factors reside. Okay. This is what I was talking about for. If all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, okay, U is equal to, except for these cases down here, U is equal to 1.0. Okay, and so an example, here would be an example that we did right here. This is my one tension member. I've applied a load like this, and I've attached the whole thing like that. Okay. Another example would be if I was connecting two wide flanges. If I had, let me see, come down here. If I had a wide flange like this, right, and I was attaching, I had a wide flange coming in, and I was attaching it to another wide flange over here. Okay. If I had them like that, if I went in and I welded this thing, if you were doing it with welds, okay, if I went through and I welded this sucker and I welded the flanges on either side and I welded the entire web, if I did that, the whole cross section. So if you looked at this thing from the side, right, if I went through and on both members I welded everything, okay, that would be a case where I've applied the load over everything and I've transferred the load over the flanges and the web, and then that case it would be U equal to 1.0. Okay. Or another way is if I bolted it, right? I could come in and have, some sort of plate here, and I have bolts here and I have bolts here, and I could have another plate across here, and I have another plate there, and I have another plate here, and I have bolts going through like that, right? If I have a bolted connection like that, as long as I connect the web and the flanges, then I get U equal to 1. If for some reason, would you look at that? I drew that last time. Good for me, Mike Berry. Okay, this is trying to show the same thing, right? If I had two things connected like that, if for some reason I didn't have those plates at the top, right? And I just was trying to connect two wide flanges, right? I have a wide flange here, right? And I have another wide flange here, and I'm trying to connect them. If I just connect the webs, right? In that case, if I'm just connecting the webs, that's an eccentric load. I'm trying to transfer the axial load just through the webs. And so immediately the flanges will not be engaged because it's just the web that's attached. And then it would take a while before it got out to those flanges, and so that's an eccentric connection, right? Versus if I apply those plates, if I put these plates across the top here, right? And then added a bolt or welded or whatever, right, on either side. Now I have the flanges connected and the webs connected, right? Or I guess another eccentric one would be is if I have those plates up there, but then I didn't have this, right? And in that case, I'm trying to transfer the entire axial load through just the flanges. Eventually it would make it out into the webs, but initially it wouldn't be in the webs, it would just be in the flanges, and it would take some more time. It would be lagged behind. And if you have one of those connections, then you get penalized, right? You have a reduction in your strength because of that. Okay? And so that's what these equations are. So this is if you're connected at if you connect the flanges and the web and the flanges, or all the elements of the whatever your shape is, if you connect everything, you have U equal to 1. Okay? If not, you calculate, it's usually going to be one of these cases. Your U is going to be 1 minus X bar over L, okay? And you're like, well, what is X bar and what is L? Well, you look right here, and they're trying to show you in these little diagrams, but this is almost exactly how it shows up in your code as well. It's really hard to kind of picture. It's really hard to picture what's happening here. Okay, and it's like, what is that a drawing of? What is this a drawing of? What is this a drawing of, right? Sometimes you can see it a little bit, like in this right here, it's the distance, right? It's the distance between the outside edge of the connection and the centroid of this angle is what it ends up being. Okay, this one's a little bit harder to see what's happening, but this is how you calculate the U. It's just 1 minus X bar over L, but what is the X bar? And what is the L, okay? And so what you do is like, I really wish I had some more information about this. So what you do is you look at the commentary, right? So this comes right out of table D 3.1. So this comes out of the specifications. If you look in the commentary for this, look at the commentary for D 3.1, you'll find a little more explanation of what X bar is and what L is. So we flip over to that. So here's a bunch of other cases as well, right? And you can look through those as you're working through your homework. Okay, but here's the specifications for chapter D. Okay, talks about some of these, right, little discussion about what the tensile strength and things of that nature. But here we are at effective net area, right? How do you calculate these X bars? And I would read through this. They've got some explanations on how you calculate X bar. Okay, but here's a graphical representation. And there is, the reason you should look back at this is it talks about, no, somewhere it says X bar is equal. Oh yeah, right here. If you read, I just recommend reading this commentary. For our case, you're going to have a case that's similar to this guy right here in your homework. And then it tells you that you could calculate x bar as just zy over a. And this describes how and why you can do that, why you can calculate z bar over a. So just a note, read through that. It's worth reading through. And I'll just take a couple minutes to look at it. But so here's a case. If I was transferring load from wide flange to something else, and I've just attached the flanges, right? I treat this thing as a WT section, and I look at what X bar is for a WT section, right? And that's what I use for my X bar, okay? If I had a channel like this, I use X bar is just the centroid of the channel. It's the centroid of this channel, so it'd be over here someplace, and that's how you calculate what the X bar is for that. This is what your homework has. It has a wide flange that you're trying to transfer the load all through just the web, right? And so it turns out you can calculate that as zy over a, but what it ends up being is you treat half the flange and portion of it. So what you do is you cut this thing in half, and you say, yeah, you cut that thing in half, and you calculate the centroid of just this half, okay? And if you looked up what X bar was for a wide flange, it would be 0 because it's just symmetric. But what you do is you look at half of it, and you say that is what it is. And it turns out cutting this thing in half is the same as doing zy over a. I thought somewhere in here there's a plot of what L was. What the heck is that? Oh, yep, there we go. So it goes on to talk about what is L. Well, L is if this thing was welded right along this length right here, L would be the length of your weld. Okay, that you would use in your calculation. So in that above example, it would be the length of the welds on the side. Okay, now if it's a bolted connection, what it is, it's the center to center distance of the out to out bolts. Okay, and so that's what I mean by that is, it's not the outside of the hole to the outside of the hole distance. It's the center to center distance between the outside hole and the outside hole. It's like, what distance are you transferring that load across, right? We're going to do an example in a few minutes where we look at that, okay, what that L is, but it's that distance right there. And so it's kind of empirical, right? For this case right here, you could look that up above. X bar would be the distance between that outside face and the centroid of that angle. The only ones that get a little confusing is when you start looking at these guys and these guys right here, how you handle it. But usually it's just the centroid of the element that you're dealing with. And then you divide it by the length, which that length is is how, over what length parallel to the load are you transferring that load over, okay? And so there's some empiricism built into that, right? And what you need that X bar for, again, you need that X bar for calculating what U is. And what is that U going into? Well, that U is going into, right? That U is going into it takes your net area and it turns it into your effective net area. And that effective net area is then what you multiply by FU and phi to give you PN. Okay? And then what you're going to do is you're going to compare this phi PN to this phi PN from the gross section. And whichever one is smaller is how it's going to fail, right? And so if this is smaller, it means that the thing is going to rip through 1 or 2 or 3 holes, whichever one you found to have the least net area, it's going to rip in that mechanism before it yields across the gross section. Versus if this one's smaller, that means it's going to yield over the gross section before it rips through this. Okay, and then we're going to have a little exercise with doing that we're going to do a little exercise with that in lab, okay, and in your homework a little bit. Okay, so the next lecture is going to be doing an example with this. Okay, and I'll do a little summary of that before the next lecture. So, like I said, it's an interesting process. You look at these limit states. You calculate the capacities of these limit states. And then you compare the smallest of which is going to be the one that's your controlling mechanism, right? Yielding of the gross section is just Fy times Ag times this. Fraction of the net section is more involved. It's just phi t times Fu times Ae. Fu is the ultimate stress. Ae is An times U. It's the net area times the shear leg factor. What is An? Well, it's the gross area minus the area that the holes take up, plus T times a Stager factor. That Stager factor is there to account for the fact that You can get an increased capacity if you stagger your holes, right? There's more area that you have to rip through, right? And what else? Oh, and then you have another mini limit state in as you go along. I don't know, is it going to rip through one hole? Is it going to rip through two holes? Is it going to rip through three holes? You have to calculate all of your ANs, and the smallest AN is the one that controls, right? And then you have the shear leg factor that you have to account for eccentricities and how in your connections, eccentricities in your connections, and the effects that would have on your capacity. All right, we will do an example next time, and this example is right here. Here, right? This is a angle attached to a plate, and we're pulling on it. Okay, and we're saying what is its capacity?